working as assistant professor in Department of Civil Engineering, UIT Peshawar. His areas of expertise are carbon composite materials for retrofitting existing structures and seismic evaluation and strengthening of the RC structures. Today, he is going to present the strengthening of brick masonry structures with FRP. Over to Dr. Samuel.
Assalamu alaikum. First of all, thank you all for inviting me, and assalamu alaikum, ladies and gentlemen. So I will now start my presentation with start sharing the screen. Okay. Dr. Saab, am I audible and also the screen is shared well?
Yes,
Hello,
we can
sir.
see your screen. Yes, we can see
Okay,
your
sir.
screen. Thank you.
Okay, so as sir has mentioned that my today's topic is strengthening of masonry structure with fiber reinforced polymer. So I will not go into the nitty-gritty detail, just I will show you that based on the expertise that you guys have gained and the material you provide to us, we use it for strengthening of masonry structure. So basically the objective of today's presentation is to highlight the scope of fiber reinforced polymer use in construction industry. And specifically, I have targeted the brick masonry structures. Why we use the brick masonry structure, as you mostly will be already familiar that in most part of Pakistan, we do use brick masonry structure. But why we do the brick masonry structures? Because there are, specifically, we can categorize it into three reasons. First one, it is relevantly simple to construct. Also, the materials are easy to transfer to remote areas. Then it is aesthetically pleasant. For example, if you see that in case of Islamia college structure, they are purely brick masonry structure without any additional arrangement. So if you have a proper brick masonry structure constructed, then you do not need any additional, for example, plastering or painting to have an elegant look of a building. And the third one that is the most important in case of our environment is that because of our hot and humid climate, we need some insulation material. So brick masonry with respect to concrete, it has a high insulation property. So therefore we prefer to have, because of these three major reasons, we prefer to have a brick masonry construction. So that's why Pakistan is the third largest country producing of bricks in Southeast Asia. The annual production is roughly 45 billion bricks per year, and the kilns that are operating are almost 18,000. But as all things, they have some positive and negative. So the negative in case of brick masonry is particularly in case of earthquakes, because the structure can withstand the load of vertical loading, but it cannot withstand the lateral loading. So therefore, we can have these sort of failure phenomena, that is the cracks within the walls or out of plane, bending of a structure. And in extreme case, we can have this sort of failure. So basically, the earthquake, the brick masonry structure is pleasant. It has a high heat insulating property. But the negative drawback of this type of construction is that it has low resistance to earthquake. And therefore, in major catastrophe, for example, in Kashmir or in Chile, we experience or we have observed devastation on a humongous scale. And this is basically the data relevant to Pakistan. In Quetta, in northern Pakistan, we have frequently earthquake activity. For example, in 1935, there was reported of 60,000 people lost their life due to earthquake. Then in 1974, another earthquake struck, but in this case, luckily the number of losses or catastrophe was less, that is 5,300. But with the increase in population and using the same sort of construction technique, that is simple masonry structure, in case of
Dr.
2005.
Samuel, sorry for interruption. We have to complete this presentation in maximum 15 minutes.
Yes, sir, I will complete it because.
Thank you.
Okay.
Thank you very much.
Okay, so basically in 2005, we have this humongous catastrophe because we have the same sort of construction that we use, and also with the increase of population. So we have this sort of failure. So later on, after this catastrophe, we have constructed this earthquake reconstruction and rehabilitation agency, and with partnership with international collaboration, they come up with this technique that is confinement or confined brick masonry structure. So basically, this is the norm after 2005 earthquake. The new construction should be built according to this technique, specifically in seismic areas or seismic prone areas. But unluckily, in case of Pakistan, as previously we have constructed only masonry structures, so therefore 80% of existing structures are of masonry structure. We have 7% of this big structure or more than 4 or 5 story structure. They are a combination of RC frame plus masonry, so we have some additional reinforcement. And we have only 13% of structure as a brick masonry structure. So we do need to improve the performance of these masonry structures to confine masonry structure. Now, the technique to use this confinement technique is very complex. So therefore, we need some strengthening technique to improve the existing structure performance. So for this, we have different treatments that are surface treatment, grout, epoxy injection. So there are numerous, but these have some drawbacks and also have some positive. But why we prefer to have FRP? Because it is lightweight, it has high strength, that is almost 5 times of steel. It is resistant to corrosion and highly versatile. So therefore, we prefer to have this sort of construction or this sort of technique. So basically, we have on a project relevant up to 10 million Pakistani rupees through HEC project. And we constructed numerous walls. First, we consider as a control specimen. This is a single room, 10 cross 12 feet room. In this case, there is no arrangement of confinement. Then in the second case, we have the confinement. And we have a third specimen in which we converted this masonry structure with the help of FRP technique to strengthen it. So what is the strengthening technique that we applied? So first we grinded the surface so to remove the roughness, because we should have a uniform bond between the FRP and the surface on which we are bonding it. So we grinded the wall, then we applied this filler material to further remove the grooves, because normally in case of brick masonry, you will have definitely grooves on one side of the wall. You can have a perfect finishing on one end, but on the other end, you will have these sort of irregularity. So then we apply a premier layer of epoxy, then we apply this FRP material in terms of strip as a bonding technique. Then we again apply a second coating. And as the major flaw in case of FRP used in construction industry, if you just overlay it on a structure, we can have only 55% efficiency of the material that we use. So in this case, we have techniques. So these are basically the three type of structure that we have tested. This one is the masonry structure. Then we have FRP strengthened masonry structure. And we have a one structure that is built according to ERA recommendation, that is confined masonry structure. And ultimately, we looked at their performance. So in terms of strength, in case of masonry, we have a 10 kilonewton lateral strength, whereas in case of FRP and confined masonry, we gain almost identical results. That is 40 kilonewton and 41 kilonewton. So it improved almost 4 times the capacity of a masonry structure. But in case of masonry structure, we do have a higher amount of displacement. We call it normally in engineering point of view as a ductility. So confined masonry structure has gain in strength and also ductility. But in case of FRP structure, we have achieved the same amount of strength, but in terms of ductility, it is but at a much higher level with respect to masonry. So we can safely say that the FRP strengthening that we have adopted, it have improved the capacity of existing stockpile almost 4 times. And as this technique require less labor, and within 2 to 3 days, we can have the structure again in service. So therefore, we can safely say that it should be the technique that should be used for the existing structures to strengthen it. So now if you have some question relevant to this topic, you can ask me.
Thank you very much, Dr. Samiullah Kazi. At the moment, we don't have any question at the moment.
Okay.
If anyone has the question, they will definitely send this question to us, and we will send this question to you later on. Thank you very
Okay,
much for
thanks.
your time.
Thanks a lot.
Thank you very much. Our next speaker is Dr. Raja Shahid Ashraf. Currently, he is working as associate professor in GC University, Lahore, and he has his PhD from Germany. He worked as a researcher in the world-leading institute like TU Eindhoven, Imperial College London, and King Abdullah University of Science and Technology. His research concentrates upon the design, synthesis, and characterization of organic, inorganic, hybrid materials for energy storage and conversion. He is also working in the area of small molecules and polymers with the close collaboration of the academic and industrial partners. Today, he is going to present semiconductor polymers for organic electronics. Over to Dr. Raja Shahid Ashraf.
Bismillahirrahmanirrahim. Assalamu alaikum. First of all, I would like to thank our organizing committee for giving me opportunity to present my work here. And today's my talk is about semiconducting polymers for organic electronics. The semiconducting conjugate polymers have been widely studied for the last 2 to 3 decades for about flexible optics, biosensors, organic field effect transistors, organic light emitting diodes, and solar cells. My today's talk will mainly focus on the organic solar cells. As we can see that in current scenario, why the solar cells are very important. For the time being, if we look into the this figure, that mainly the electricity is currently being produced from coal and natural gas, which are from the fossil fuels and have greenhouse gases emissions. So renewable resources could be one of the major options for the developing country like Pakistan to have electricity being generated without any concern to the environment. On this slide, I would like to show the best research cell efficiencies reported by the NREL, which are being certified by the different labs. And the efficiency so far, if we look in that, silicon solar cells is on the top with the better efficiencies, followed by the perovskite solar cells. And organic solar cells are also doing substantially good here, and the efficiency have been reached up to in last 5 years from 10 to 18 to 19%. So before going into the detail about the organic solar cells, I like to mention here that what kind of the device architectures are being currently followed in the organic solar cells. These are 2 types of device architecture here. One is bulk heterojunction and the other one is the bilayer. In bulk heterojunctions, we mix in the photoactive layers, we mix 2 materials together and make one film. But in case of the bilayers, we just use both the materials separately on top of each other. And because of the feasibility and easy to use and having the better results, the bulk heterojunction is the main type of the architecture being followed by the most of the researchers. And so in this talk also we will do all the devices which are mentioned here are being done by the bulk heterojunction solar cells device architecture. So what happens in this bulk heterojunction cells? As the photoactive layer is very important, when we put light on these devices, what happens after the absorption of the light, excitons are generated, and then these excitons they transport and move towards the different electrodes. However, there are different parameters which influence the photocurrent generation. I mean, they always said microstructure, especially the domain size of donor and acceptor part in this system, and how the molecular packing, domain connectivity, and interfacial energetics, and along these the absorption spectra of these photoactive materials, whether they are absorbing in the visible enough in the visible light, or they cannot absorb much, and and the exciton diffusion length. I mean, the excitons can generate, can reach to the respective electrodes easily or not. There has been a substantial work done on the light absorbing electron donor materials, and about a lot of research groups have reported different polymers which can be used as an electron absorbing material, electron donor materials for the solar cells. But these one, the poly-3-axial thiopene was one of the materials being widely used in the early research in the solar cell, but due to poor absorption in the visible region, have not shown much consideration later on. However, these new material polymers which were synthesized later on, they have shown considerable absorption in the visible region, and have shown along with the acceptors have shown the substantial improvement in the performance, and good solar cells devices have been reported. And the other part which alongside these donor materials was used is the electron accepting materials, that we need two counterparts. One is the electron donor and the other is the electron accepting. Fullerenes are one of the well-known electron accepting materials. They are very efficient to three-dimensional structures, and they have shown a significant contribution in the OPV development. However, the limiting factor for these electron accepting materials is that a high cost of the production, and there are challenges to the purification of these materials. And also they show limited absorption in the visible and near infrared spectrum. Finally, it is for the final one is that this is more also that it's very difficult to tune their energy levels. So I mean, we have only few kind of materials which works very efficiently with these acceptor, but it's challenging to get the materials done for these materials. So keeping these things for these electron accepting materials, the researchers had decided, okay, let's try some different materials which is easy to tune and can be utilized as an electron accepting material in the solar cells. So we and the other research groups started working on the different type of acceptors, and we were able to, I would say, get new generations of the electron acceptors, which are cost effective and easy to pure and scalable. And there is a good chance, possibilities to tune the absorption of these materials. So once we have the new types of the electron acceptor material, which here is different type of the structures of these non-fullerene acceptors being reported, with the power conversion efficiencies being reported about 10 to 15% by different research groups. So once we have these electron materials, electron accepting materials, we decided, okay, let's see that if we can go back to poly-3-axial thiopene, which is the simplest of these polymeric electron donor material. Why P3H? because it's very easy to synthesize and scale and possible to scale up to multi-kilogram scales. It's wide band materials. Have shown good charge carrier mobilities. And more interesting is that this material has been already tested for the large printing area techniques, showing which and it shows good compatibility of these techniques. However, for this material, because if we look at the structure, it shows a very limited photocurrent in the visible region, and so we need something which can absorb in the visible region and can be utilized with this well-known material, and might be able to get these organic solar cells for the commercializable products in the future. So what we did, our group started to work on the different type of the NFA molecules. We designed few materials and tested them in our lab with the poly-3-hexyl thiophene. For our initial designs, which we got these two non-fluorine acceptor molecules, we got the comparable performances with that of the fullerene acceptors. We got good open circuited voltage, but we have the limited photocurrents, and that was that because these non-fluorine acceptor molecules, they were still not absorbing enough in the visible region of the spectrum. So we went back again in the lab and decided to modify the structure of the non-fluorine acceptor molecules. So what we did is that we changed the middle core from the indinofluorine to indocyanothiophenes. So by putting two thiophenes on the periphery inside on the middle core units, and not only substantially increase the absorption from 450 to about 700 nanometers, and this one gave us a very substantial improvement in the solar cells performance as well. So the performance has power conversion efficiencies has been improved from 4.5 to 6.5%. So which was one of the best results, solar cells results reported with the poly-3-hexyl thiophene. But for us is that, okay, if there is any other possibility, we can improve further. We can get better results with these solar cells or not. We decided to try something different. So at that moment, we decided to see that if we can improve the morphology by adding a third component. I mean, instead of using two components, we decided to go for ternary solar cells, using three components in one layer. And by careful looking into the energetics of these molecules, we used two acceptor molecules and then we used P3HT as the donor molecule, polymers, and with the devices. And we were able to get one of the best results reported with P3HT, which we later reported in the Nature Materials, and we were able to get the efficiencies above 7%, which was a record at that time for the poly-3-hexyl thiophenes. And when we tested this same kind of the approach with the different polymers, we were able to get even about 11 to 12% efficiencies. So that we have shown that we can by careful design and then modification in the device architectures, we can improve the results, which started from the 4%, and at the end we were able to get around 8% efficiencies. Further, as if we like to use these solar cells for the commercialization or in the future, it is quite important to know about the stability of these devices. So we tested these materials, not only that, okay, at least we did at different device area, but also their stability as well. So we placed these materials in the shelves and tested under the light without any encapsulation to see that if these materials can be processed without any interruption in the industrial setup. To our surprise, what we have seen that where we have these ternary components. They show the best stability, and they were quite stable even in the shell with limited drop in the performance over 1200 hours. While in case of under this light, they shows the stability up to 100 hours. And with encapsulation, we think these materials can work up to many years without any problems. So as we have got good performances for these organic solar cells, but there is one more thing, that because we are using a poly-3-hexylthiophenene, a polymer in these devices. So as we know that the polymer shows the batch-to-batch variations, and it's very difficult to control their PDI and molecular weights. Also, catalytic impurities can play their role in the device performance, and they can be a challenging situation for the scalability of these materials. And generally, it's known that the high molecular weight polymers usually work better. So to test these things, what we did is that we used 6 different kinds of the molecular weights of poly-3-hexylthiophene, and we tested with the non-fluorine acceptor being synthesized in our lab. What happened is that we didn't see good results with a low molecular weight or with a very high molecular weight fractions. Instead, we saw very good results from in the medium-sized molecular weight polymers, showing very good efficiencies, about 7%. For even a binary blend. Instead of ternary, we were able to get about 7% from a binary blend with a careful choosing the right batch. To further test these things, we also gone into looking into the morphology of these blends by using the transmission electron microscopy. And if we see here, we can see that where the P3HT's molecular weight was around 35 kilodalton. There is the donor and the acceptor, both components are well distributed and have a smaller domains compared to the very low molecular weight P3HT or very high molecular weight P3, where we can see the big phase separations, which is not ideal for the best performances. So I think so my talk over, and I would like to stop my talk here. Finally, the conclusion. We have seen that we see the best performance from the polyhexylthiophene with a molecular weight range of between 20 to 40 kilodaltons. And we also have seen that we can tune the absorption energy levels of these non-fluorine acceptors, and which can help to improve the solar cells efficiencies. And finally, here is a slide which shows the organic solar cells being roll-to-roll printed by the Heliatech company in Germany with a module efficiency about 13%, and being used. And these devices are being used in the different buildings in Germany as well currently. So hopefully these kind of the solar cells, we can integrated solar cells in the buildings we can see in Pakistan in the near future. Once again, I would thank for everyone who was listening, and also I like to acknowledge my research group and my collaborator from KAUST and from Imperial College London and University of Cambridge and UCL. And thank you very much. Assalamu alaikum.
Thank you very much, Dr. Rajat Shahad Ashraf. We have a question up here. What kind of other application other than organic electronics we can use these semiconductors?
Thank you. I think so for these organic semiconductor polymers, we depends on the structure because what kind of the structure you have designed, they can be used for the transistors. They have been actively be used in sensors, and very recently people have started working on the bioelectronics. So these materials, by changing the side alkyl chains to hydrophilic, because these alkyl chains are hydrophobic, what we have used in solar cells. But if you change it to the hydrophilic ones, they can be very efficient devices being used for the organic bioelectronics currently. And they can be one of those materials which are very compatible to the skins, and you can use them without any problem. And some recent results have shown already a very good performance by using P-dot based polyethylene diethoxythiophene based polymers for these bioelectronics.
One of the another question, Dr. Rajesh. One of the researchers just sent me a message and said that he's also working on polythiophene. And he said that it is difficult to prepare this, synthesize this polythiophene as compared to polypyrrole and polyaniline and something like this. And are you? He said that, how did you get the high purity polythiophene?
I think so. If you are an organic chemist, I think so. The polythiophene is usually made by Grimm method. This is Grignard methodologies, and nowadays I think so companies are using the flow reactors. I mean, you are using one component for the polymer synthesis, and they have already shown companies in US and even in Germany that this polymer can easily be synthesized in multi-kilogram scales without any problem, and even it's possible to get the right batches as well, because it's one component, I mean the one monomer with two functionalities, and you can get a regio-regular system. I understand what that person means, that the regio-regularity is an issue, that the alkyl chain where it is coming, but that can also be controlled by the methodology by which you are preparing. I think so it's quite trivial because we usually do it for the master students and they can synthesize this polythiophene in our lab.
Yes, you are right. Thank you very much, Dr. Rajesh. Thank you very much for your nice talk and informative session.
Thank you.
Thank you very much.
Assalamu alaikum.
Assalam.
Now, I would like Dr. Asim Lai Khan to present his talk on sustainable polymeric and composite membranes for industrial separations. Dr. Asim Lai Khan is currently head of chemical engineering department at Composites University Lahore campus. He completed a master from Chalmers University of Technology, Sweden, and followed it up with PhD and postdoc from KU Leuven, Belgium. During his tenure at KU, he did pioneering work in the area of high throughput experimentation in membrane-based gas separations. Dr. Khan is founder of Membrane Systems Research Group and established a world-class laboratory carrying fundamental and industrial projects. He has published more than 80 papers with over 3,300 citations. He was recently listed in the top 2% scientists worldwide by report published by Elsewhere. He is editorial board member of Chemical Engineering Research and Design, Carbon Capture Science and Technology, and early career editorial board member of Separation and Purification Technology journals. So over to Dr. Asim Lai Khan.
Thank you very much for the kind introduction. The topic of my talk is Metal Organic Framework-based Mixed Matrix Membranes, Future Directions for Gas Separations. Let me take a couple of minutes to introduce my research group that is named as Membrane Systems Research Group at Composites Lahore. This group was established in 2013, and since 2013 we have managed to acquire multiple national and international grants. As a result of those, our applications are now featuring membranes for CO2 capture. We are also producing membranes for industrial separations, and one of the major area of our application of membranes is water and wastewater purification. We are also focusing on surface treatment of membranes, membrane characterization, and producing novel membranes that can reduce fouling and control it. The Membrane System Research Group at Composites is also affiliated with the Pakistan Membrane Society. And for more information about our research group, you can visit our website, that is membranecui.com. Now moving to the technical outline of my presentation, I will start with general introduction. Then I will talk about the general challenges associated with the separation processes, mainly gaseous separations, future directions in the area of membrane-based materials, and then I will talk about few studies that we have done at Composites Lahore on membrane-based gas separations. And finally, I will conclude my presentation. In the last century, we have seen so many advancements in the field of technology. We have seen industrial evolution, whether it's textile sector, whether it's automation and control, whether it's process industry, chemical industry, fertilizers, refineries. We have seen so much of growth because of these technological developments. However, it wasn't until early 1970s when this classic by Rachel Carson was published that mankind realized that all these developments, all these mankind activities do come at some cost. And one of the major costs is environmental degradation that is leading to severe destructions. One of the major challenges associated with the environmental degradation is global warming. We have seen in the past century and in the past couple of decades how the global warming has increased, how greenhouse gas emissions has increased, and when it comes to the emission of greenhouse gases, carbon dioxide takes the major share. The majority of the emissions produced by the combustion of fossil fuel, by anthropogenic emissions, up to 65% of it is carbon dioxide. So one of the repercussions of increase in CO2 emission is the increase in average temperature of the earth. As a result of it, we have seen unequal distribution of temperature at earth. This is leading to droughts in some countries, melting of glaciers, rising of sea levels, and all of it is contributed by the anthropogenic emissions of carbon dioxide. So there is a need to find sustainable ways for CO2 capture. Among the different technologies that are available for CO2 capture, we need a sustainable comparison to find out the way that is most sustainable. Now there are several techniques or there are several technologies that are available for CO2 capture. Way back in 2010, we carried out a comprehensive review of the different technologies that are used for CO2. And on the basis of that analysis, we concluded that membrane separation is by far the most sustainable. Why? Because it is a simple process, it involves low capital cost, it is highly energy efficient, and once a membrane is produced at a lab scale, it is relatively easy to upscale it. So obviously, membranes are the sustainable future for CO2 capture. And when it comes to membrane performance, there are few properties of membranes that are most crucial. One of the property is permeability of the membrane or the flux that we can drive through the membrane. How selective is the membrane? What is the level of purification that we can obtain from a membrane? And how robust is a membrane? That is, what is the mechanical stability? What is the thermal stability? And what is the lifetime of a membrane to which it can operate? So an excellent membrane would be the one that shows very high permeability, very high selectivity, and it has long lifetime. Despite all these advantages of membrane, there are certain challenges that are faced by membrane researchers. And one of these challenges was presented by Robison in 1991 when he plotted all the available materials, which are mostly polymers, whether it's glassy polymer or rubbery polymer, for a certain gas separation. In this case, the application is CO2 removal from natural gas, CO2CH4. On y-axis, you can see it's the selectivity of the gas, and on x-axis, it's the permeability or the flux of the gas. Mr. Robison concluded that all the materials that have been discovered so far, there exists a trade-off. The materials that have high selectivity, they have low permeability. The materials that are highly permeable, they have low selectivity. And he said that in order to commercialize the membrane, in order to take over the adsorption and competing technologies, we have to develop membranes that show performance in the region above this negative slope of line, which he called as upper bound. So a material that can be commercialized for membrane-based gas separation should be the one that should show simultaneously high selectivity and high permeability. So this is the target region for membrane researchers. What are the future directions for next generation membranes? These are the three areas in which the scientists or researchers are mostly focusing on their work. We can work on task-specific tailored polymers. We can functionalize, modify polymers to make them highly permeable and highly selective. A lot of effort is being directed towards mixed matrix membranes. Mixed matrix membranes are the membranes that combines polymers with inorganic fillers to make use of both properties. And another effort is being done in the area of ionic liquids or deputectic solvent immobilized membranes. At Composites, at Membrane System Research Group, we are working or focusing our effort in all these three different areas. We are working on tailored and functionalized polymers. We are working on ionic liquid-based membranes, and a lot of our effort is being dedicated to mixed matrix membranes, where we are using high-performance porous fillers in the polymer matrices to make mixed matrix membranes. As I mentioned previously, these membranes combine the low cost and easy processability of polymers by adding highly selective and permeable porous fillers. So as a result, there is a composite generated which comprises of a polymer matrix in which we have a dispersion of inorganic fillers. A number of different fillers have been previously used, such as zeolites, silica, carbon nanotubes, metal organic frameworks. However, the major problem with the commercialization of mixed matrix membranes is that there are certain problems which are associated with the dispersion of fillers in polymer matrices. Because polymer is an organic part, these silica zeolites are inorganic and they don't really like each other. As a result, usually there is a micro-wide or a space generated between an inorganic filler and a polymer matrix, and because of these gaps, because of these micro-wides, the selectivity or the separation of the membrane reduces because the non-desirable gas also passes through this gap. So as a result, the target is to make defect-free mixed matrix membranes. One of the material that we are aiming for in making mixed matrix membranes is MOF. MOF are metal organic frameworks that are simply a combination of metal ions with organic linkers, and when these metal ion and organic linkers are combined together under certain reaction conditions, they make a three-dimensional framework that has surface areas as high as 10,000 meters square per gram. Already in the literature, these metal organic frameworks have based membranes have shown potential even beyond the upper bound. So MOF are the way forward because they comprise of these organic linkers. Because of their organic linkers, there is a better compatibility with the polymer matrix, leading to high performance mixed matrix membranes. At Composites, we have carried out several studies using these metal organic frameworks. I will go through few to give an idea of how these MOFs are behaving and what are their performance. In one of the study, we use zirconium based metal organic framework, which is also called as UIO66. This metal organic framework shows very high porosity, very high surface areas. It's very stable both thermally and chemically. However, what we did in this study, we functionalized it with sulfonic acid group with the objective to induce CO2 philic groups. So we wanted to increase the properties of this UIO66 very well studied, very well known MOF by using post functionalization with sulfonic acid groups. We were able to produce very well defined porous MOFs. We went ahead, instead of using post functionalization of sulfonic acid groups, in this study, in the extension of this study, what we did, we introduced CO2 philic groups such as amines, sulfonic acid groups, and we did this by using this functionalization within the MOF. So what we did, we used modulation approach. So we used linkers comprising of these CO2 phthalic groups, and we introduced them in the framework to produce modulated UIO 66 based membranes. And finally, we synthesized membranes and tested them for gas separations, which I will just share in few slides. Another material that we focused on our work on was biomorph. Biomorph name derives its name from adenine based linker. Adenine is produced from purine, so it's a natural source. That's why the name biomorph. It's a cobalt based morph that has shown in absorption studies very high CO2 uptake, leading to multiple Lewis basic sites, and as a result CO2 can act as a Lewis acid, and we can have better good interactions between CO2 molecules and these biomorph molecules. We were able to produce very nice flake shaped biomorph crystals which showed very high crystallinity, and we subjected them for CO2 capture. Finally, the last material that I will talk about is BIT72 based morph. It is a highly stable aluminum based morph with a surface area of more than 1000 meter square per gram, and this material has also showed very high post combustion CO2 capture properties. What we did was we collaborated with University of Liverpool with Professor Shintu's group, and we carried out post modification using oxygen and nitrogen plasma to induce oxygen and nitrogen based functional groups with a bit to enhance CO2 capture properties, and we were able to obtain very nice pebble shape based morphs. Moving on to the gas separation properties of these membranes, we found out that these membranes showed very high CO2 and CH4 selectivities. Most of these morphs were also highly permeable. As you can see in this graph, which was plotted on Robinson upper bound, the BIT72 based membranes showed performance just touching the upper bound, and plasma treated morph showed performance even beyond the upper bound. So these studies gave us direction that by using organic linker based morphs, we can generate mixed matrix membrane that show very high permeability, very high selectivity, and these membranes obviously show performance beyond the target region for membrane researchers. The functionalized UIO 66 membrane based membranes showed very high selectivity. However, there were some decrease in selectivities which can be overcome by using modulation approach. To conclude, we can say that mixed matrix membranes are indeed a way forward for CO2 capture, whether it's post-combustion capture, whether we want to separate CO2 from natural gas or biogas. However, so we cannot simply try a just new morph and a new material and test its properties for CO2 capture. There is a need to very carefully select morph by a molecular simulation study, and obviously once a molecular simulation study is concluded, that we normally do in collaboration with other research groups, the selected morph can be further tuned, functionalized to overcome the trade-off between permeability and selectivity. I would like to thank my research group, PhD and master's students who carried out these studies, excellent work that they have done. I would like to thank them. I would also like to thank Higher Education Commission, Pakistan Science Foundation, and other international agencies that have funded our research that I have been able to present today. With this, I would like to thank you for listening and would welcome any questions. Thank you very much.
Thank you very much, Dr. Asim Lake, for your nice presentation. Really, it was a very technical presentation and guideline for those students and researchers who are working on this membrane technology. If you are available, we can ask one or two questions from you. Dr. Asim Lake. Okay, thank you for your presentation. We will gather these questions and we will send these questions to you for their answers. Thank you very much.
Now, I would like to invite Ms. Iffatul Ain to present his research work on dope-dyed polyurethane electrospun nanofibers. Ms. Ifatul Ain, she is currently a MS student at Mehran University of Engineering and Technology, Jamshoro. Over to Ms. Ifatul Ain. Ms. Ifatul Ain, can you hear me?
उनका माइक तो नहीं ऑफ पूछो दोबारा
Ms. Ifatul Ain, please start your presentation. Share your screen.
Yes, sir. I'm sharing my screen.
Ms. Ifatul Ain, is there any problem? Your screen is
The
not shared
screen is
yet.
visible or not?
No.
Sir, screen is, sir, I shared.
Can you close it and then open it again?
Sir, I have shared the screen.
No, it is shared. You can start, please.
Okay, sir. So, first of all, I would like to extend my humble thanks to Second International Conference on Polymers and Composites 2022. And my research work is development of low triangle polyurethane electrospun nanofibers with dispersed dye. And this work, this is my research master's project, and this work is also the part of NRPU project 6866. So let's have outlook on outline. So this is introduction, then research gap, aims and objectives, experimental work, research methodology, testing, results and discussion, and in the last conclusion. So first of all, introduction. Basically, electrospinning was invented as a patent to manufacture continuous nanofibers. Electrospinning is a facile and efficient technique which uses electric field to produce nanofibers. And in this process, we use high voltage electricity to the liquid solution and align the solution to extrude from a nozzle. This process offers several advantages, including versatility and simplicity. Inexpensive variety of polymers can be used, variety of nanostructures can be constructed, and higher productivity. So why dope dyeing? So basically, dope dyeing is a technique in which colored thermoplastic fibers are manufactured. In this method, dye is added in spinning mill and then filaments are extruded. So dope dyeing is widely known method for dyeing textile substrate. Following are the benefits which can be achieved by using this dyeing methods. First of all, it is time efficient, economical, ecological, excellent dye dispersion, outstanding color and uniformity. So these are the researchers which reported on the dyeing of nanofibers. So the dyeing of polyurethane nanofibers, polyurethane polymerized fibers. This is a synthetic thermoplastic polymer used for stretchable material, and polyurethane fiber is popular. Its high rubber-like stretchability and is usually known as spandex fiber. So polyurethane has been dyed deep of news with and without salt. The dyes. So these researchers operation again, engineering scaffolds, drug delivery, protective clothing, and shape
Miss
memory.
Ifat,
So research gap. Research gap is the dyeing of polyurethane fibers and its nanofibers.
can you please shift on presenter
sir.
mode?
Hello.
Can you shift your slides on presenter mode? Full screen.
Previously reported by conventional procedure, and this work is to be further developed on dope dyeing of polyurethane nanofibers with dispersed dye by electrospinning process. So the aim of my project is development of dope dyeing of polyurethane nanofibrous mats using polyurethane polymer with dispersed dyes. And the objectives of my research work is developing dope for colored polyurethane nanofibers with dispersed dyes. Second objective is electrospinning of the dope to fabricate weed-free polyurethane nanofibers. And the third objective is optimization of the dope and electrospinning process through color evolution and characterization of colored polyurethane. Experimental work. So the experimental, these materials were used to carry out my research work. First of all, polyurethane polymer. I have used two dyes, dispersed red and dispersed blue. And the solvents which I have used were dimethyl formamide and methyl ethyl ketone for the dissolved polyurethane polymer. So research methodology, this research methodology was followed throughout my thesis: preparation of polyurethane polymer, then preparation of polyurethane dope, then electrospinning of weed-free polyurethane nanofibers. After that, optimization of dope solution, and in the last, testing was done. So this machine was used for the fabrication of undyed and dope-dyed polyurethane electrospin nanofibrous mats. And this machine is available in Color Research Lab, Department of Textile Engineering. So the testing, so the color strength and colorimetric values of dope dye were assessed on data color spectrophotometer, and the parameters of machine was set at the sample aperture 9 mm, illuminant D65, standard observer is 10, and ultra wide and specular component is included. So dope dye sample for the color fastness to 1, whereas color fast dye very pretty length. So this SAM testing machine and dope dye and discussion. So this is basically this figure shows the photographic images of undyed and dope-dyed polyurethane nanofibrous mats, which were successfully prepared by electrospinning method. The photographs clearly shows that dyed nanofibrous mats produce a good color buildup. As a result, they may be utilized for sports, casual, and the fashionable clothing. So this graph presents the effect of curing temperature on color yield of the dyed polyurethane nanofibrous mats with 1.5% of the dye for 90 seconds of the curing. The figure shows that by gradually increasing the curing temperature, color yield was improving up to 100 degrees centigrade. and afterward it started declining for both dyes. That may be due to the possible deformation of the polyurethane nanofibers after 100 degrees centigrade. Whereas the color yield of dispersed blue 56 was better than that of the dispersed red, and that may be because the lower molecular weight dye diffuses and fixes better than the high molecular weight dye. So this figure presents the effect of curing time on color yield of the dyed polyurethane nanofibrous mats with 1.5% of the dye at 100 degrees centigrade of curing. This figure depicted that both dyes shows improvement in color yield as the curing time increases. So, but the optimized curing time for both dyes was 60 seconds. This may be because longer exposure to high temperature creates burning effect and deforms the nanofiber. So this is the effect of dye concentration on color buildup. This figure presents the effect of dye concentration in the dope solution on color yield of the dyed polyurethane nanofibrous mats cured at 100 degrees centigrade for 90 seconds. The figure shows color buildup with increasing dye concentration, and the saturation level occurred at 1 degree for the red dye and 2.5% for the blue dye. The better color buildup of the blue dye is attributed to the better diffusion and fixation of the lower molecular weight dye. So this is the table for the effect of dye concentration on colorimetric values. So this table shows that decreasing lightness value with increasing concentration of both dyes is evident, that indicating the increase in the color depth. For red dye, A value is negligibly changing and B value is increasing with increasing dye concentration. This shows that red dye builds slightly yellow as the concentration increases, whereas for the blue dye, A value is increasing and change in blue, B value is negligible with increasing dye concentration. So this shows that the blue dye builds slightly redder as the concentration increased, whereas the chroma was remained similar with increasing dye concentration for both dyes. So this is the table for which shows the color fastness to washing and light for the optimized dope dyed polyurethane electrospin nanofibrous mats with both dyes at optimum conditions. So these results shows that the overall color fastness of the dope dyed polyurethane nanofibrous was not very good. However, the color fastness of polyurethane electrospin nanofibrous mats was good when dyed with same dyes but the pad dry cure method. So this ultimately shows that the dispersed dye is embedded properly into the polyurethane polymer when doped in a solution. So this may be improved when if we dope that if the doping is carried out in the molten polymer instead of the polymer solution. So these are the images which shows the smooth morphology of the nanofibers with no beads, indicating that the polymer concentration of polyurethane, the selected solvent system and employed electrospinning parameters were successful. Whereas figure B and C shows the morphology of the dope dyed polyurethane electrospin nanofibrous mats and the undyed nanofibrous mats was similar. So this shows that the dope dyed and pure nanofibers were unaffected by curing temperature and the dyes were properly diffused into the fiber using the polymer system. So these are the conclusions of my project research work. It is concluded that dope dyed polyurethane electrospin nanofibrous mats can be successfully prepared by electrospinning method, whereas the SAM images exhibit that morphology of undyed and dope dyed polyurethane electrospin nanofibrous mats was almost identical. Moreover, color yield gradually improved with a simultaneously rise in the concentration signifying good color yield. Maximum color yield for blue dye is 12.43, whereas for red dye, it was 9.97. The optimized post-dope dyeing parameters were curing temperature 100 and the time was 60 seconds. However, the overall color fastness properties were not very good. So these are the references of my thesis, and this is all about my presentation. Thank you.
Thank you, Ms. Afifatullah. It's a nice presentation. At the moment, we don't have any questions. So if we receive any, we will forward to you. Thank you, Ms. Afifatullah. Now, I would like to invite Ms. Asifa Sattar to present his research work on digital inkjet printing of regenerated cellulose electrospun nanofibrous mats with reactive inks. Miss Asifa Sattar is MS student at Mehran University of Engineering and Technology, Jamshoro, in the Department of Textile Engineering. So, Miss Asifa Sattar, please start your presentation. Ms. Asifa Sattar, please accept the request to join as a panelist so that you can start your presentation.
Can you hear me?
Ms. Asifa, please start.
Screen is visible to you?
Asifa, screen is visible to us. You may start.
Sure, sir. Assalamu alaikum. Ismi Asfa Sattar. I'm a student from Mehran University of Engineering and Technology. My research is on digital inkjet printing of regenerated cellulose electrospun nanofibrous mats with reactive inks. And this is the part of master's project, and it is a part of NRPU 6866 project, whose principal and co-principals are Dr. Shamshad Ali and Dr. Awais Khatri respectively. Here is the outline of my presentation: introduction, experimental work, results and discussion, conclusion, references. Introduction. As nanotechnology, as my research is related to the nanofibers, so first of all, I want to give a little bit background and introduction. Nanotechnology is a unique way of producing material with distinct and significant properties. And the most significant characteristics of nanofibers are their high porosity, high surface area, unique interconnected structure, which make them fascinated candidate for various applications. These are used for many applications like tissue engineering, biosensors, for textile, functional textiles, smart textiles, so on. As the textile industry has been recently recognized as a new driver of the world economic growth and inspired by the emerging boom in nanofibers and smart textiles, apparently a wide range of industries are predicted to benefit from the revolutionary fibers and smart textile in near futures. So, as along with the functional properties of nanofibers, their aesthetic properties are widely important. So many researches are also has been reported on coloration of nanofibers. My research is on the digital printing of nanofibrous mats. So digital printing is one of the modern technology that developed rapidly because of its rapid response to fashion patterns and satisfactory printing effects, and due to its precise pattern, no wastage of print waste, lesser amount of inks is used as compared to the other methods. It is one of the satisfactory printing method. So I use cellulose nanofibers to print. Cellulose is itself an abundant polymer which is mostly used in preparation of membranes. Cellulose, here we regenerate the cellulose from cellulose acetate by electrospinning of cellulose acetate, that followed by the deacetylization in alkaline bath. Cellulose itself is a kind of hydrophilic material that exhibits excellent properties as breathability, air permeability, and biodegradability. The aim and objective of my research, the aim is development of digital printing process with reactive inks for regenerative cellulose electrospun nanofibrous mats to enhance the aesthetic appearance of nanofibrous mats. These are the objectives of my research: preparation of regenerative cellulose nanofibrous mats through deacetylization of electrospun bead-free cellulose acetate nanofibrous, development and optimization of preparatory process and post-treatment of inkjet digital printing for cellulose nanofibrous mats with reactive inks. Testing of printed regenerative cellulose electrospun nanofibrous mats for color yield, color coordinates, color fastness, and morphology. Experiment for research methodology. Here it is the research methodology. First, we prepare polymer solution, then we made electrospun nanofibrous mat, then further process, then digital printing and testing. Here are the materials which I used for my research: polymer, cellulose acetate, solvent, dimethylformamide, and acetone to dissolve the cellulose acetate. For deacetylization, sodium hydroxide is used, and subtract cellulose acetate electrospun nanofibrous mats, regenerated cellulose electrospun nanofibrous mats. And for pre-treatment of the mats, sodium carbonate, sodium bicarbonate, and urea are used. And 4 reactive inks are used to print the cellulose nanofibrous mats with digital printing. Cyan, magenta, and yellow-black inks are used. Cellulose acetate, CA polymer preparation. So first of all, I prepare a cellulose acetate polymer solution by using 18% weight by 8, and solvent ratio was 2:1 to dissolve. First, I put the 18% weight by weight polymer solution into the as solvent, acetone, and amide to mix the solution. The mixing time was set around 8 to 24 hours to get the homogeneous mixture. After making a polymer solution, we moved to electrospinning process to make a nanofibrous mats by electrospinning process of CA polymer. Here, during electrospinning, 12 kV high voltage was set, 12 centimeter tip from tip to collector was fixed, and feed rate was 0.2 ml per hour. Syringe which I use is needle gauge 23 and 3 ml syringe. After making the nanofibrous mats, I air dried them for 24 hours to remove the extra residue. After making cellulose acetate electrospun nanofibrous mats, so to regenerate cellulose electrospun nanofibrous mats, we use an deacetylization process. For this, I dipped the cellulose acetate nanofibrous mat into the 0.05 molarity sodium hydroxide solution for 30 hours to get the regenerated cellulose electrospun nanofibrous mats by removing acetyl group from the CA cellulose acetate nanofibrous mats. The thickness was achieved is around 60 to 90 micrometer. As a period to digital inkjet printing, the regenerated cellulose electrospun nanofibrous mats were treated with alkaline solution which contained urea, sodium carbonate, and sodium bicarbonate, as alkali is required for ionization between the hydroxyl group of cellulose and the reactive group of reactive inks. So we pre-treat the samples period to the digital inkjet printing. And the solution, pre-treatment solution was applied by spray technique onto the sample here, as it is visible in second image, the application of pre-treatment solution, then air dry, then we move to the digital printing. But before digital printing, we optimize the concentration of chemical agents, for example, for such as urea, sodium carbonate, sodium bicarbonate. We use different concentration by fixing the post-treatment parameters, like fixation temperature was around 160 degree and fixation time for 90 seconds to get the optimal recipe for the pre-treatment process. Further, we move digital printing. For digital printing, Epson L382 digital printer was used to print the cellulose nanofibrous mats. A pattern of 10 by 40 mm for each color was set, and sample size was around 40 by 40 mm. Resolution was set 600 dpi by 600 dpi, and the fixation temperature was around 160 degree, and fixation time around was 90 seconds. First, we use a paper. We paste the sample of cellulose electron nanofibrous mats onto the paper to support the printing process. After printing, we post-treatment fixation. After digital inkjet printing, the CMYK printed cellulose electrospun nanofibrous mats were placed into the oven dryer for fixation to fix the reactive dye into the cellulose in nanofibrous mats. For post-treatment, we also optimize the parameters such as temperature for fixation and time for fixation, which is we set to get the optimum parameters for the fixation process. After samples were fixed, the washing of process was done to remove the unfixed dye, unfixed reactive inks from the printed samples of cellulose electrospun nanofibrous mats. Then move to the testing. We did these testing for printed samples. We check color yield, K/S value, CIA, color coordinate, LAB, and chroma U, color fastness to washing by using standard ISO 105C10 2016, color fastness to light BS 106 1990 UKTN. And unprinted and printed sample were examined through the same test to know the morphological difference between the samples. Result and discussion. Here are the graph which shows the concentration of pre-treatment chemicals. So effect of concentration of pre-treatment chemical agents on the color yield of printed NMS. As I mentioned that we use different concentration of pre-treatment chemical agents. Sodium bicarbonate.
Please try to conclude it within 5 minutes as we are short of time.
Sure, sir. So we get the optimum concentration at 15 gram per liter sodium carbonate, and sodium carbonate at 5 gram per liter, and urea at 100 gram per liter. These are the concentration of the chemicals we will use for the further process and as an optimal recipe for treatment process. Here are the effect of fixation temperature on the color yield of a printed samples. So we set different temperature from 150 degree to 200, and we get the optimum maximum color yield at 160 degrees Celsius. Effect of fixation time on color yield on printed sample. We use different timing to get the optimum time for fixation process. So all samples show the maximum color yield. All CMYK, cyan, magenta, and yellow black show the maximum color yield at 120 seconds. Here are the testing results. Color fastness process of properties of digital inkjet printed samples. Here is a light fastness result, and all the samples shows the good, excellent light fastness as mentioned in the table, and also good washing fastness properties. Color yield and color coordinates of the digital inkjet printing. So here the printed samples K by color deed is mentioned and LAB values, chroma U is mentioned. The black color show the maximum color yield, then magenta, cyan, then magenta, and then yellow samples. These are the scanning electron microscopy images. Here, these results, SAM result shows that the before the cellulose acetate, after regenerated into the cellulose fibers, there is no difference in the structure. We get the smooth after printing and before printing, and the bead-free structure. And these are the visual images of the samples, printed samples of nanofibrous mats. Conclusions. As digital inkjet printing of the regenerated cellulose electrospin nanofibrous matched with reactive ink can be successfully done for the first time. All the pre-treatment and post-treatment parameters were optimized, and we get the optimum concentration of sodium bicarbonate at 15 gram per liter and sodium carbonate at 5 gram liter and urea at 100 gram per liter, whereas optimized temperature and time were 160 degree and 120 second respectively. All the samples, cyan, magenta, yellow, and black digital inkjet printed samples show the excellent color fastness properties, and morphology structures also shows that they were smooth and bead-free. There were no effect was after and before printing was visible. These are the references of my presentation. Thank you.
Thank you, Ms. Asfa Sattar, for your nice presentation. So on digital ink printing. Now I would like to invite Mr. Dilshan Purna from University of Moratuwa, Sri Lanka, to present his talk on study on pressure transmission patterns of medical compression textiles with miniaturized air bladders.
Good afternoon to you all. Can I hear you?
Yes, Mr. Dilshan, you can start, please.
Yeah, good afternoon to you all. I am Dilshan Purna from University of Moratuwa, Sri Lanka. Here is the presentation on study on pressure transmission patterns of medical compression textiles with miniaturized air bladders. And here is the content slide of this presentation: chronic venous disease, severity of the chronic venous disease and associated cost, treatment options for CVD, methodology, results, and conclusion. Introduction. Chronic venous disease. Chronic venous disease is considered as the most prevalent vascular disease affecting to the lower limb, and it is defined as any morphological or functional abnormalities of the venous system. For examples, telangiectasis, blue vein, edema, varicose veins, and venous ulcers, pigmentations. Those are the examples for the chronic venous disease. So, severity of the chronic venous disease and associated cost. It is estimated that the prevalence of the varicose vein is ranging between 10 to 30% of the worldwide population, and it was 5 to 30% among the adult population in the developed countries. In the United States, the annual treatment cost for the treatment of leg ulcers around 3 billion with the loss of 2 million work days. In countries with improved healthcare system, The overall treatment cost for the chronic venous disease is around 1 to 3% of the total budget allocated for the healthcare system. The global market for the treatment is expected to grow US dollars 290.59 million in 2016 to 396 million in 2025. Hence, there are a lot of treatment methods are available for the chronic venous disease. Among them, compression therapy is considered as the compression therapy is most widely used for the treatment of chronic venous disease. In compression therapy, an external pressure is applied to the limb. Once the external pressure is applied, decrease the diameter of the major vein, resulting increase the blood flow. It's a kind of restoring the calf functional calf pump unit. So in compression therapy, basically there are two major categories: passive compression treatment methods and the active compression treatment methods. In passive compression treatment methods, a constant pressure is applied, and active compression treatment method, a variable pressure is applied. Under the passive compression treatment method, there are two methods. There are two examples. Mainly, there are two examples: medical compression bandage and the medical compression stockings. In medical compression bandage, it's quite difficult to apply a pressure gradient from ankle to knee, and it could not be able to apply a uniform pressure around the limb circumference. And when consider the medical compression stocking, it's quite difficult to donning and doping, as well as both of these methods could not be able to apply a uniform pressure around the limb circumference. In order to overcome those limitations, active compression treatment systems were introduced. However, single bladder cuff and the multi-chamber cuff are the mainly considered under active compression treatment methods. In single bladder cuff, the pressure is applied using a one bladder. Hence, it was unable to apply a gradient pressure from ankle to knee. And also, it's quite bulky and heavy. To overcome those limitations, multi-chamber cuffs were developed. It means there are more than 3 cuffs. Hence, it could be able to apply a uniform pressure from ankle to knee. However, both of these methods could not be able to apply a uniform pressure around the limb circumference. Hence, the novel active compression devices were developed using active material like dielectric elastomer actuators, shape memory polymers, shape memory alloys. However, even though they have developed using active compression devices, they could not be able to apply a uniform pressure around the limb circumference, as its tension was generated due to the deformation of the active material. Hence, a novel research has been carried out to develop an active compression device which could apply a radial force in response to the pressure exerted by air volume trapped inside the mini bladder. And they have shown that the developed active compression device could apply a uniform pressure around the limb circumference. It was done by placing an AMI airpack sensors around the limb circumference such that it coincides the mini bladders, and then measure the AMI pressure values. And they have shown that all the pressure values are same. However, they haven't studied the pressure transmission patterns with various parameters like varying side length, thickness, gaps like that. Hence, this study is to study the pressure transmission patterns with various side length and the thickness using numerical simulation. So in order to numerically simulate, first we need to validate experimental result with the simulation result. So that we need to develop an active compression device. So the active compression device was developed with 3 layers: top, bottom, and the fabric layer. Here the fabric layer was introduced into this active compression device to reduce the inflation of the bottom side, such that we can increase the pressure transmission percentage. So there are 2 mini bladders were developed using high modulus fabric, and the same high modulus fabric bonded with the carbon fabric. And then for the top and bottom layer of the mini bladder unit was developed using high plastic materials like silicon, based on its biocompatibility, low modulus, and the stress effect compared to the other material like rubber and PU. So here is the mold that we have used to manufacture the mini bladder unit, and here the mold 1 and part A and part B are those things. And part B was placed inside the part B, and then it looked like as this, and then the silicon material which was produced by mixing part A and part B 1:1 ratio was poured into this and keep it for the curing. And once it's cured, the top layer was peeled off. Then, in order to produce the entire mini bladder unit, this is the mold number 2 we have used. The part B was inserted in the part A, and then, as mentioned previously, the silicon material was poured into the mold halfway, and then placed the fabric layer onto it, and then again silicon material was poured into the mold such that it completely filled the mold. And once it was halfway cured, the previously manufactured top layer was placed on the top surface of the bottom layer, and then keep it for the curing. Once the curing is done, the final mini bladder array, as you can see here, this was peeled off, and here is the manufactured mini bladder array top and bottom view. In order to determine the pressure transmission characteristics of the manufactured mini bladder array, this was the experimental setup that we have developed. And here is the perspex tube, and the developed mini bladder array was wrapped around the perspex tube, and it was inflated by a syringe. And to measure the interface pressure, three AMI pressure sensors were placed on the perspex tube such that it coincides the mini bladder array. And to measure the applied pressure, the other end of the tube was connected to the pressure sensor, and it was read by the computer. And then once the experimental setup was done, we need to develop the numerical model. So here is the geometric model for the mini bladder unit and the acrylic tube, and here is the acrylic tube, and here is the mini bladder array, which consists of 3 layers. As you can see here is the top layer, and the gray one is the fabric layer, and the red one is the bottom layer. And those are the dimensions that we have used in the geometric models. And the side length was varied 1.5, 2 and 2.5, and the thickness was varied 5.5, 6, 6.7. Once the geometric model was developed using SolidWorks, it was imported into the ANSYS workbench to numerically model the inflation behavior of the mini bladder array. And those are the material parameters and the models that we have assigned. Out of these parameters, silicon one and the knitted fabric bonded with the carbon fabrics parameters were experimentally determined, and the acrylic tube was determined using the literature. And for the meshing the models, we have do the mesh analysis and determine the suitable sizes, suitable mesh size for that. Once meshing was done, we need to assign the boundary and loading conditions. As I mentioned earlier, the mini bladder was a 3-layer device. So between top and fabric layer bonded, and the fabric layer and the bottom layer also bonded, and the interface between the top layer and the exterior surface of the hollow cylinder was considered as the friction. And between the surface marked as A and B, considered as the frictionless, and the bottommost surface was considered as the friction. And the applied pressure, all the interior surface of the air chambers, including the air channels, were defined as the surface of the range of pressure applied, and the applied pressure was varied from 0 millimeters to 10 millimeters of further. And here are the results. As you can see here, these are the pressure transmission characteristics of the mini bladders. Here, the pressure transmission characteristics was initially increased and then gradually decreased. And here, the pressure transmission characteristics was initially increased and reached to a plateau level. Here, this one is corresponding to the mini bladder array manufactured with the high modulus fabrics, and here this one is corresponding to the mini bladder array manufactured with the
Mr.
high
Dilshan,
modulus.
due to limited time, please try to conclude the presentation in maximum 5 minutes.
Okay.
Thank you.
Then we have go with this mini bladder array. To determine the material parameters, textile fabrics were determined. Textile fabrics were tested under ASTM 5035, and Young's modulus were calculated by drawing a tangent line to the stress strain curve, and those are the results of the Young's modulus. And to determine the material parameters of the hyperelastic model that we can use to determine the strain behavior of the silicon material. Here you can see those are the YEHO first, second, and third order model fit with the uniaxial test data. In here, graphically and the statistical data conclude that the YEHO third order model is suitable for the determine the strain behavior of the silicon material. And this is the comparison of experimental results with the numerical results. As you can see here, simulation results had more than 95% agreement with the experimental one. Hence, we have used this model to determine the pressure transmission patterns with a different size and thickness. And here is the pressure transmission percentage with different sizes. As you can see here, once the side length of the mini bladder was increased, the pressure transmission percentage was decreased. However, for each mini bladder, when the thickness is increased, the pressure transmission was increased. And those are the conclusion. Around 55% of the applied pressure is transmitted onto the treated surface, and the average pressure of the simulation had more than 95% agreement with the experimental results value obtained from the MI sensors, and the percentage of pressure transmission decreased as the bladder size increased, while it was increased as the thickness increased. Thank you.
Thank you very much, Mr. Dilshan. Due to time limitation, at the moment we cannot take the questions, but we will send these questions to you if there is any question related to your presentation.
Thank you.
With this presentation, this is the end of the second session of the second day of second international conference on polymer and composites. We have a short break of about 1 hour, and we will start the third session sharp at 2 o'clock. Thank you very much for all the participants.